Okay, for this video I've been asked to help out with question 2, which comes from exercise 3B of the extension 2 textbook from Cambridge. So we're in complex numbers territory, and the question says use similar methods to the previous question to show that, and then we've got 3 parts A, B and C. Part A is about cosine of 4 theta, part B is about the sine of 4 theta, and then part C is about the tan of 4 theta, and we've got various trigonometric results for each. It's interesting to note that we're being told to use similar methods to the previous question. Now, I haven't been asked to help out with question 1, but if we just take a quick look, question 1 tells us to use the identity cosine 3 theta plus I sine 3 theta equals cosine of theta plus I sine of theta all to the power of 3, to use that identity to derive some results. So essentially the hint is we're going to use the Moivre's theorem, and the classic technique that is going to help us here is when we expand the right hand side, the power there using a binomial expansion, you can then equate real and imaginary parts to get various identities, and that'll really help with part A and B. And then part C, tan of 4 theta, really we can work out using the results from part A and part B, because we know that tan of x, tan of any angle, is equal to the sine of that angle divided by the cosine of that angle. So that's basically the technique. So let's get going. We'll start with part A, and as I mentioned, we're really going to be making use of de Moivre's theorem with the angle in question being 4 theta. So what we'll want to say is we can know by de Moivre's theorem, which I'll just call DMT, de Moivre's theorem, that the cosine of theta, the cosine of 4 theta plus I times the sine of 4 theta, we know by de Moivre's theorem that that is equal to the cosine of theta plus I times the sine of theta all to the power of 4. And then the key, as I mentioned, is we take this right hand side and we expand it using the techniques of binomial expansion, which if you're working through the extension 2 syllabus, then it will essentially be assumed that you've learned about binomial expansions in extension 1. So I'm just going to take that as given. I won't labour that too much. But basically we can say that the right hand side, we're going to be able to expand that. If I just, as a side note, let's just note, just in case you're not fully clear, the binomial expansion, if we pick any value x plus any other value y to the power of some power n, we can write that as the sum from k is equal to 0 up to n of, and I'll write this as nck x to the power of n minus k, y to the power of k. And you may see that as x to the power of k, y to the power of n minus k. Either format's fine because of the symmetry of the expansion. But basically here, wherever we see x, we're going to put in cosine of theta, and wherever we see y, we're going to put I sine of theta, and then wherever we see n, we're going to put the number 4, and that will allow us to expand the right hand side. So let's go do that now. I might just erase this and start a bit lower so I've got enough space. But we're essentially saying that the right hand side is equal to the sum from k is equal to 0 up to 4, since for us n is equal to 4, of nck, or 4c 4ck, sorry, and then for us x is cosine theta to the power of to the power of 4 minus k, and then I sine theta to the power of k. So we're just going to loop through for all the values of k. K is equal to 0, 1, 2, 3, and 4. So we can say if we're starting at k is equal to 0, we'll get 4c0 Cos theta to the power of 4 minus 0 is 4. And then I sine theta to the power of 0. And then we'll get having k is equal to 1, so we'll have 4c1 cosine of theta to the power of 4 minus 1 is 3 times I sine theta to the power of 1. And then we'll add to that 4c2 cosine theta to the power of 4 minus 2 is 2. And then I sine theta to the power of 2 plus 4c3 cosine theta to the power of 4 minus 3 is 1. And then I sine theta to the power of 3. And then finally plus 4c4 cosine of theta to the power of 4 times I sine, cosine of theta to the power of 4 minus 4, or to the power of 0, plus I sine theta to the power of 4. So that's basically the nuts and bolts of the binomial expansion. To clean this up, the first step we'll do is we'll just kind of deal with all these powers, and particularly being careful about the powers of I, because whether we have I to the 0 or I to the 1 or I squared being equal to negative 1 and so on, we'll get either 1, I, negative I, or negative 1, and that's going to end up determining what our real and imaginary parts are. So let's clean this up. 4c0 gets us 1, and then we'll have 1 times, or I'll just write, actually let's not worry about the 1 times, let's just write, so we'll get 1 times cos to the power of 4 theta, and then the I sine theta to the power of 0 just gets us 1 again. And then we'll add to that 4c1 is 4, and then we'll have cos cubed theta, and then I sine theta, because that's all to the power of 1, and then 4c2 is 6, and then we'll have cos squared theta, I squared sine squared theta, and then we'll add to that 4c3, which will be 4, cosine of theta, that's just to the power of 1, and then I cubed sine cubed theta, and then 4c4 is also 1, cos theta to 0 is 1, and then we get I to the 4 sine to the 4 theta. And as I briefly mentioned, now the key is to think about our i's and the various powers of I, and thinking about what we end up with, and that will help us with our real and imaginary parts. So this is going to be equal to, and we will end up with cos theta to the power of 4, and then we'll have the I just remains as I, so plus 4I cos cubed theta sine theta, and then the I squared becomes negative 1, so that will become negative 6 cos squared theta sine squared theta, and then the I cubed we can think of as I squared times I, and that then gives us negative I, so we'd have minus 4I cos theta sine cubed theta, and then I to the power of 4 we can think of as I squared times I squared, or negative 1 times negative 1, which becomes positive, so we just end up with a plus sine to the power of 4 theta. Now, for part A specifically, we're looking at the cosine of 4 theta. Now, if we look at Moivre's theorem, the cosine of 4 theta is the real part of the left-hand side. So we can say the real part of the left-hand side will be equal to the real part of the right-hand side, and we've just expanded the right-hand side here. so that we can now think, well, what are the real parts? So it's anything that doesn't have I in it. So in this in our case, it would be the cosine of 4 theta. It would be the minus 6 cos squared theta sine squared theta. And then it would be the plus sine to the power of 4 theta. So let's say, therefore, by equating the real parts of the left-hand side and right-hand side, we can say that cosine of 4 theta is equal to, and we get our cos to the power of 4 theta minus the 6 cosine squared theta sine squared theta plus sine to the power of 4 theta. And let's just scroll up to double check. What we were asked in our question, cos to the power of 4 theta minus 6 cos squared theta sine squared theta plus sine to the 4 theta. So that is as required. That is what we were being asked to show. So that's part A all done. Hopefully you followed that. Now, because we've done all this work here with our binomial expansion in part A, part B actually becomes very simple. So for part B, we're just going to say by equating imaginary parts, and then we just get to basically our solution. So if I just get a highlighter, I sine theta in our left-hand side is the imaginary part. So it's really sine theta is the imaginary part because it's what sits next to I. So that's our left-hand side, and our right-hand side, the imaginary part, would then become, or the imaginary parts would be the 4i cos cube theta sine theta, and then the minus 4i cos theta sine cubed theta. But just to be clear, we don't include the I in that. The imaginary part is everything that's let's undo that. The imaginary part is everything that sits around the I. So just to be really clear, I'll just see if I can erase. Yep, and the imaginary part is specifically everything that sits next to the I. So just in case I've caused any confusion there, I'll make that really clear. So there should be an I there. So here it's the 4 and the cos cube theta sine theta, and then it's the minus 4 cos theta sine cubed theta. So those are the imaginary parts. So now let's equate those. So we end up with sine of 4 theta being equal to 4 cos cubed theta sine theta minus 4 cosine theta sine cubed theta. And again, let's just double check that is as required. So we wanted to show sine 4 theta 4 cos cube theta sine theta minus 4 cos theta sine cubed theta. So that also is as required. Not a lot of working for part B once we've done all the hard work in part A. Panic boom! And as I mentioned earlier for part C, again, we actually get to make use of the results we've just found in parts A and B because we know that the tan of 4 theta is equal to the sine of 4 theta divided by the cosine of 4 theta. And we've just found out what each of those are in parts A and B. So now we can just substitute those in and hope that we can simplify to what we're trying to get towards, which is 4 tan theta minus 4 tan cube theta divided by 1 minus 6 tan squared theta plus tan to the 4 theta. So we see that in this result we want everything in terms of just tan. So that we'll need to keep that in mind as we substitute in our results from part A and B. and then go about simplifying. So let's do that. Let's substitute in parts A and B. So sine 4 theta, we know is 4 cosine cubed theta sine theta minus 4 cos theta sine cubed theta. And that's all going to be divided by cos to the 4 theta minus 6 cos squared theta sine squared theta plus sine to the 4 theta. Okay, now the question is, what do we do here? And again, as I mentioned above, we want everything to be in terms of tan theta. And again, making use of our generic result, so where we started with this result, we know is tan to the any angle, I'll just say tan x, is equal to the sine of x over the cosine of x. We want to make use of that again, and the way we can do that is if we divide both the numerator and denominator by cosine to the power of 4 of theta. So if we're dividing top and bottom by that, we're not changing the expression, but what you'll see is we'll end up with sine divided by cosine of the same power of the angle, and that's going to allow us to get everything in terms of tan. So I'll just write this out in full. So we'll have 4 cos cubed theta sine theta divided by cos to the 4 theta minus 4 cos theta sine cubed theta divided by cos to the 4 theta, because we're dividing the top by cos to the 4 theta, and then all of that is divided by cos to the 4 theta on cos to the 4 theta, and then minus 6 cos squared theta sine squared theta on cos to the 4 theta, and then plus sine to the 4 theta on cos to the 4 theta. So that's essentially what we've done by taking this step here. And you may ask yourself, well, how did I know to do cos to the 4 theta? Why not sine to the 4 theta? And it's because, again, coming back to this result here, we know we want the sine in the numerator and the cosine in the denominator. So we want the cosine to the highest power to be what we divide by. That's basically the kind of rule of thumb you can think about. We want to pick the highest power here, which in our case was to the power of 4. And we divide top and bottom by the cosine of that power. And that generally will get you what you need in terms of converting everything to tan. And we're going to see that right now, because let's now break all this down. Here the cos cubed theta in the numerator and the cos to the 4 will simplify. Here the cos theta in the, maybe actually I'll just use a different color, might help make things clear. So maybe I'll use blue here. So the cos cubed theta will cancel out with the, and we'll end up with just a power of 1. Here the cosine theta in the numerator will cancel out, and we'll be left with cos cubed theta. Here the cosine to the power of 4 will each cancel to leave us with 1. And here the cos squared theta will cancel out, and we'll end up with cos cubed theta in the denominator. And then we've got the same power here already. So let's just write that out. So we get 4 times sine theta over cosine theta minus 4 times sine cubed theta over cosine cubed theta, and all of that is divided by 1 minus 6 sine squared theta over cosine squared theta plus sine to the 4 theta over cosine to the 4 theta. And now we can make use of our identity about tan being sine over cosine. So we'll get 4 tan of theta minus 4 tan cubed theta divided by 1 minus 6 tan squared theta plus tan to the 4 theta. And let's go back up to the question and see, is that as required? 4 tan theta minus 4 tan cubed theta divided by 1 minus 6 tan squared theta plus tan to the 4 theta. So that looks pretty good. That is as required. Alright, so there you have it for that question. Really, as I mentioned right at the beginning, the essence of this question, which we're kind of hinted at when we're told to use the similar methods in question 1, is all about taking de Moivre's theorem, expanding the right-hand side using our binomial expansion, and then really the key, the technique is first equating the real parts, then equating the imaginary parts, and then for tan, it's just using this identity here, which hopefully you learned quite a while ago, and it's an oldie but a goodie, basically. So, yeah, that's the key, and maybe this bit here, kind of knowing to divide top and bottom by cos to the power of 4 theta, where the power of 4 is the highest power that we had in the expression. That then allows everything to simplify to just being in terms of tans, various powers of tan. That, again, might be new to you. But hopefully you've been able to follow along with all of that, and you're now comfortable that this is something that you could do on your own if you had to. So, yeah, there you have it. Tick boom.